Hi, this is Mrs. Lemke, and we're going to take a little journey today. This is one of my most favorite lessons, so I'm very, very excited that we're doing this together. And the way that this lesson is formatted, it's supposed to kind of lead you to the topic. So sometimes as a teacher, you make the decision to kind of be like, okay, this is the main idea, here you go. And you kind of present the main idea, and then after the main idea, you do a lot of practice and application. That's one kind of lesson. That's not today. This lesson is much more, I'd say, kind of like reading a mystery novel. So you start out and you're not necessarily sure why certain things are being mentioned, but you're just kind of trusting the author and rolling with it. And eventually you're like, oh, I see all of those things, you know, that thing from chapter 3 and that thing from the end of chapter 5, like all of those wove together and ta-da. That's like today. Okay, so I hope that you have fun with it. We are going to be discovering something that's called a Maclaurin polynomial, and when it has an infinite number of terms, it's called a Maclaurin series. And then the broader category is what is called a Taylor polynomial or a Taylor series. So there are going to be times that I'm asking you to do something and just roll with it. Mystery novel. Okay, so the first few questions on here, I'd like you to just try. There's 4 questions or 4 tasks. The first one is to make a graph. That's not too hard. The second one says what power series has, what is the power series for that? You might be a little confused about that, so I'm going to give you a little hint off the top, and that is to think about this formula related to that. Okay, so that's my little hint. And then if you understand number 2, then number 3 will make sense. It won't make sense without number 2, though. And then in number 4, it says, well, number 4, everything built. It's like a mystery novel. So number 4, you're going to take these 4 things up here, and instead of sum number 1, sum number 2, think of it as like y equals, and graph those 4 functions. Okay, so if you're really lost, you only would be able to do these first 2, which would be like graph y equals 1, graph y equals 1 plus x, and then there'll be 2 others, hopefully. And then I want you to make a graph of all of those down there. Okay, so I'm going to ask you to pause. And I definitely, I know I say this in like every video when I talk about pausing and trying by yourself, but this is actually super important because, you know, think about reading a mystery novel if you just read the end. It wouldn't be that good, right? So you need the buildup. You need to see why all the threads connect. I promise it's going to be worth it, okay? Big mathematical journey. So come back here. I'll come back here, and you will pause and try 1 through 4, and then we'll have a little conversation, okay? Do the best you can. Okay, so the function f of x equals 1 over 1 minus x is a hyperbola. It has a vertical asymptote at 1. It has a horizontal asymptote at 0. It has those 2 branches. Swell. The power series question, hopefully my hint helped you see. I'm thinking there of that sum of a geometric formula, right? Power series act in structure like geometric series. And so I'm going to think of my first term as the 1, my constant ratio as x, and then I would have the power series that I wrote there in blue, 1 plus x squared plus x cubed plus x to the 4th. Which means if I'm doing partial sums are where you just take part of the infinite sum. So the first term, the first and second term, the first, second, and third term, etc. And then I asked you to look at a graph of those. Now, the by hand graph is admittedly messy. So I'm going to show you on Desmos because I think my showing you that, first of all, you don't have to suffer my poor ability to draw, but it's also going to help us answer question 5. So you already have your own graph there, and that graph is just great. And then what I want us to talk about as we look at my graph is what are you noticing about each graph? Like as we add another term, what's going on? Okay, so I'm here in Desmos, and the window that I picked for recording this doesn't work perfectly, and then it's cutting off some of my equations, but you have the same picture in front of you, so it's okay, I think. So the black graph is the original function, 1 over 1 minus x. And then here is the first partial sum, just y equals 1. Here's the second partial sum. I'm going to turn the first partial sum off. Here's the next one, maybe. There we go. Okay, so that's 1 plus x squared. That's 1 plus x squared plus x cubed. I'm going to call that the third partial sum. And I didn't ask you to do this, but this is the fourth partial sum. This is the fifth partial sum. So now let's just go back through that one more time. Okay, so what happens as I get close, like as I add more and more terms? How are these partial sum guys related to our original function from whence they all came? Well, it seems to me like in this vicinity that I'm kind of indicating, whoops, on the graph right now, right around 0, kind of up here, each successive curve is fitting that black graph a little bit better, right? Like this guy back here, this was just the second degree equation, and it seemed to be fitting pretty well. But then you get to the fourth degree equation, and you see how that red curve is even a little bit tighter. Now, it's not tight everywhere, right? Down here at -8, this black graph is so far away from the red curve. But there is a section for which they're close together. So, back to our question. What do you notice about each successive graph? Well, I would say that each additional term brings the resulting graph closer to that black graph, that original function, at least in part of the graph. I mean, not all over, right? We did say that. It's fitting really well in this area around the y-axis, and it's fitting less well elsewhere, right? Out here at 8, the graph is way far from this red curve, right? Those are not close together, but there is a section right in here where the red and the black really are like almost on top of each other. You might say they kind of converge. Da-dum-dum. Plot clue. Okay, so here's some magically appearing writing for you. This is what I just said out loud. So each additional term brings the resulting graph closer to the original function in the part of the coordinate plane that appears to be roughly between -1 and 1, you know, in that vicinity around 0. It seems like we're getting closer and closer. All right. Now, there are some directions up above that I did not put into the slide presentation, but I just point out that each partial sum is a polynomial. So if you look back, our original function, this guy, this hyperbola, it's not a polynomial. It's not like particularly ugly as a function, but it isn't indeed a polynomial. But this, that is a polynomial. Well, actually, it's a series, but it's like an infinite polynomial, right? So wouldn't it be nice if everything could be a polynomial? Why would we like that? One of the first rules that you learned in taking derivatives was the power rule. Isn't that a lot easier than, say, chain rule or quotient rule? Gosh, it would be nice if everything could be based in polynomial land, because polynomials are awesome. So let's see. Let's see if this will work for other, maybe uglier functions. Okay? Now this one isn't particularly ugly, but you know, we have to start with the more simple examples. All right, so this question says, what is the equation of the tangent line? Now, when I read this, finding an equation of a tangent line, I have alarm bells go off in my head, and the alarm bells remind me that every single time ever that those are the directions, I need a slope and I need a point. Those are the two things. If I have those two things, I can write the equation of a line. So let's read the rest of the sentence now that the alarm bell stopped. What is the equation of the tangent line to y equals e to the x at x equals 0? And it's an equation that goes through 0, 1. Oh, so there's my point. How do I find slope? Well, slope is a derivative, right? What's the derivative of e to the x? Still e to the x, so that's good. So if y prime is e to the x at x equals 0, the value of y prime would be e to the 0, and e to the 0 is 1. So my slope is 1. So now I can write the equation of my tangent line using point slope form of a line, or I can tidy it up a little because that looks kind of awkward. There we go. Okay, so that is my line. Now, at x equals 0, does the concavity of the tangent line match the concavity of e to the x? Well, I don't really understand that question yet, but I know e to the x looks like this. And I know that tangent lines don't have concavity. They're lines. They're straight. They don't curve up. They don't curve down. They don't curve. They're straight, right? So I'm going to say no. Lines don't have concavity. E to the x is concave up, though. Okay, so clearly they aren't the same. Now, big challenge question I'm going to leave you with for a minute, okay? This is going to be something I want you to think about yourself. Can you make a polynomial that has concavity to match e to the x at x equals 0 while still maintaining that the slope at 0 is the same? So back here, tangent lines work, and I'm going to use this picture here to just illustrate. Here's my tangent line. Right here, I'm just going to call them black and green for a minute. The black and the green share a point, 0, 1. The black and the green share a slope at 0. They have the same slope. So they share a point and they share a slope. That's what a tangent line does, okay? Now what I'm asking is for you to take that green line and bend it. Bend it to be a function so that the point is shared, the slope is shared, but they also have the same concavity at 0. Okay, this is a time to pause and think and try. Okay, so in my mystery novel analogy, this is a major plot turning point. That's where we are right now, okay? So understand that all the writing I have here in black is referencing this black curve e to the x. And we are now trying to make something kind of like the green tangent line, except not a line. We want it to match point and slope and concavity. Okay, so that line needs to curve and fit a little better. So what I've noted is that all of the derivatives of e to the x are themselves e to the x. In fact, that's why we're using this as an example. F of 0 is 1, therefore. F prime of 0 is 1. F double prime at 0 is going to be 1. F whatever prime of 0 would have to be 1. So I want to make a polynomial that has that same attribute in that my polynomial at 0 has to be 1. My first derivative of this polynomial at 0 has to be 1. The second derivative at 0 of my polynomial has to be 1, right? Those values that I just wrote in green need to match the black, okay? So if I try to build such a polynomial, the constant term needs to be 1 to get that to happen, okay? And then we already worked with our tangent line example earlier, and that was our tangent line, okay? And that's going to allow, when I take the first derivative of this, the 1 will go away, and its derivative would just be 1, and that would satisfy this. Okay, so what I'm picturing there is p prime of x, right? You're taking the derivative of this statement. The derivative of 1 is 0. The derivative of x, 1x, is just 1, and that's going to allow that part to be true. Okay, now I need to think about what if I were taking a second derivative. Okay, so the second derivative at 0 has to be 1. If what I thought first was maybe I just add this, that causes a problem. Because what happens when I take a derivative of x squared is I get 2x. And I don't want that 2 there. I need this to turn out to be 1. So how can I compensate for that? Oh, if you found this, you can feel very good about yourself. Okay, if you didn't, that's okay. All right, but this is what we do. Okay, now when I take the second derivative, I will get of this, right? The second derivative evaluated at 0 will be 1 because the 1/2 compensates for that 2 being there. Okay, so challenge. What about if we wanted the third derivatives at 0 to match? Well, I can see pattern, right? That's what we love about math is we can see pattern. So I'm going to call this polynomial degree 2. Put a little subscript there. And now let's look for polynomial degree 3. And so as I was saying, I can see pattern. And I bet you can too because you're good at math. So here is our tangent line. And if I wrote that as polynomial degree 1, that's really this, right? If I put it in a different order, 1 plus x. Polynomial degree 2 was 1 plus x plus 1/2 x. Polynomial 3, 1 plus x plus 1/2 x squared. Okay, now I'm going to do something incorrect here. That is what most people think at this juncture. And that's fine, right? We all, in solving the mystery, have a suspect, and sometimes that suspect is not actually the murderer, right? Okay, so we need to figure out why that's not right. It's close. It's the best wrong answer that there is. But why is that not quite it? So I know it's going to be thinking, right? This is going to be a hard pause to actually do, but I think you're up to the challenge. Pause and figure out what is wrong with that. And I will give you a hint, a further hint. The x to the third part, totally right. It's the coefficient. Figure out why the coefficient doesn't work. Okay, so the way that I would have approached this, knowing that there was a mistake, was to say, okay, let's look at the mistake. This is what I wrote down. I told you this part was incorrect. And I took some derivatives. And I saw, oh, okay, I'm going to end up with a 2, but I really need it to be a 1 in order to do what I want, right? I want it to match the derivative value of e to the x at 0, which is always 1 for any ordered derivative. And so I have an extra factor of 2, so I need to compensate for that. So like here, right, in the previous question, we compensated for that exponent of 2 by having a 1/2. We've already taken care of the 3 by having a 1/3, but maybe I need another, like 2. I need to compensate for the 2 and the 3 that happen in the successive derivatives. So what's the coefficient? I need to have a 2 and a 3 here. So isn't that 6, right? A factor of 2 and a factor of 3. 2 times 3 is 6. Intriguing. I just love this. Where is this headed? It's exciting. Okay, so here's the big question. Is there some kind of pattern that we can define for this e to the x thing every single time? So e to the x, each polynomial had 1, each polynomial had an x, and then as we added successive terms, we had this. So in other words, what's the pattern? Right? So going back here, when I had x to the 1, you could, right, like these had 1s on the top. This is like 1 over 1. Maybe that helps. You can see my denominator here is a 1, my denominator here is a 2, my denominator here is a 6. I don't really know what's going on here. Maybe I could write that as x to the 0. And what would be the number in the front? I mean, it has to be equivalent to 1. I'm kind of confused about that. So this looks like 1, this is 2, this is 2 times 3. maybe I could think of that as 1 and 2 times 1 and 3 times 2 times 1. What's the pattern? Okay, if you're not sure, pause so you have time to think. If you're with me, I think you know that the next term here is x to the 4th, and then a 1 over 24. How on earth did we get the 24? We got the 24 because it's 4 times 3 times 2 times 1. What is this idea? Haven't we seen this somewhere else in life? Back in like second year algebra? That's called 4 factorial. 3 factorial, 2 factorial. Technically, that's 1 factorial. Also, how about this? 0 factorial? What's 0 factorial equal to? Oh, it is equal to 1. It's because factorials get used, or one way to think of it is factorials get used to say how many different ways are there to arrange something. So if I have 4 elements, there are 24 ways that I can put those 4 elements in a row. If I have 0 elements, how many ways are there to put those 0 elements in a row? Sort of a philosophical question, but it makes sense to me that the answer is 1. See my 0 things? See how they're organized? It is the one way that 0 things can be organized. I don't know, it seems kind of philosophical, doesn't it? So I think we found the pattern, guys. This is fantastic, okay? So we could, in sigma notation, write this because this goes on forever, and say we have an infinite sum. You always find that infinite sum by having a factorial number on the bottom. Start at 0 because this first term has a 0 factorial here. Have an x to that power. So when I had 2 factorial, I had a 2 here. When I had 3 factorial here, I had a 3. And then technically, now this part is a little obscured with this particular example, but all of our 1s up here are actually because we were looking at the value of derivatives. And we were looking at the value of those derivatives at 0. Okay, so the f with an n here means the nth derivative. So f with a little, like 5 means 5th derivative. So you take a derivative, a factorial, and a power. Oh my gosh, you guys, I kind of feel like crying because this is just such an awesome topic. I hope you really come to love it. I hope you're not just really super frustrated right now, but there's a lot of math here, and that's what's so exciting. Okay, so that's the big pattern. That's the big ta-da. Okay, so can we apply this pattern that we just found to the first 4 derivatives of cosine at x equals 0? Okay, so I know that I need to structurally have a derivative value at 0, a factorial, and a power of x. That's what I just found. Okay, that was the big idea. Put that like in a little box for myself. Okay, so let's try that out. So our function is cosine. So f at 0 would mean cosine of 0, which is 1. I need to find f prime, f double prime, f triple prime, and the 4th derivative evaluated at 0. Actually, I think I'm going to write x. I think it would be better, I think your notes will be better for yourself if we write x's here. Sorry, anyone writing in pen, you now just are mad at me. Okay, so let's first write down derivatives and then we'll evaluate them. Okay, so our function is cosine. The derivative of cosine is negative sine. And then finish out this list and evaluate at 0. Okay, magically appearing writing, just trying to keep the video not horribly long. So wrote all the derivatives, evaluated all the derivatives at 0. Okay, now we're going to say, well, that means that the cosine function, and by the way, is the cosine function a polynomial? No, it's not. Okay, so the cosine function would be exactly equal to, not estimating equal to, exactly equal to the following. Take this first term here. Here's my derivative, my first derivative. So first derivative, first factorial, x to the first. Then second derivative, 2 factorial, x to the 2. Then third derivative, 3 factorial, x to the 3. See how it's very patterny? Okay, and if you're bothered by those zeros, I'm doing that on purpose just to make sure that we see the pattern, okay? And then the fourth derivative is 1, 4 factorial, x to the 4th. This pattern goes on forever. And if we come back and do some cleaning, this term is 0, this term is 0. So if I come back through here now, I'd have 1 minus 1 over 2 factorial x to the 2nd plus 1 over 4 factorial x to the 4th. The next term is going to be minus, because I can see these as alternating, 1 over 6 factorial x to the 6th, and so on. Oh my gosh, the pen. All right, so if I were to look at this and say, let's try to write this in sigma notation, I'd say I have an alternating sign situation. If I start at 0, I can start my exponent on the sign alternator at 0, because that will give me a positive first term. And then all of these exponents are even numbers. Even numbers are multiples of 2. The exponent here and the factorial here are the same number. So this exponent of 2n means this is 2n, it's 2n factorial. Boom. That, my friends, is the infinite series that is a polynomial that represents exactly cosine. Now, let's just take a minute and just back up. I know I'm making the video long. Cubby, I'm sorry, you're going to be so mad at me. But back up for a quick sec, okay? Think about where cosine even comes from. You start with a triangle, a right triangle. You come to realize that all triangles that have proportional sides have the same ratio relative to their angle. Like the angles, the proportion of sides is the same. Okay, I'll just say it that way. And then adjacent over hypotenuse. You decide to call that cosine. And then you take that cosine function, or you take cosine and you make it into a function. You say, okay, I'm going to take all these different angle measures and put against that, okay, these are my different angles. Here's my angle. That's supposed to be a theta. I take my different angles and I keep track of the ratio of sides as that angle changes. So as this triangle stretches and shrinks in different ways, right? So as that, as you go through the unit circle, right? That's really what I'm talking about. Okay, as we swing through the unit circle and we get different angles, what is the ratio of sides that you'd have in those reference triangles? And you keep track of that. And you get this curve. And you say, okay, we're going to call that the cosine curve. And then that thing that's called cosine is related to this? What? Isn't math the best, you guys? I just can't stand it. All right. So, major, big time question. Major. And then we're done for the day. I can barely speak. I'm so like blown away. Okay. Can we generalize the pattern that we just saw in the cosine function, the pattern that we just saw in e to the x? Can we generalize this pattern for matching however many derivatives we want with any function that's centered at 0? I really want you to try this. See if you can write it generically. Okay? See if you can. Pause. It's time to pause. Try it. Okay. So I hope you got this. That would be so amazing, okay? So if you are basing everything around x equals 0, which is what we did in all of the examples we just did, then your polynomial that you build starts out with, okay, let's have the function and the polynomial we're building match at 0. Let's have their first derivatives match at 0, so they have the same slope. Let's have the second derivatives match at 0, so they have the same concavity, and so on down the line. Now, this just ends at the nth degree term. So we would say that that is a polynomial of degree n, so that's my notation. And we call this a Maclaurin polynomial. So Maclaurin polynomials are based on 0 and have this structure. They are Maclaurin polynomials if they just end at degree n. They're Maclaurin series if they go on infinitely long, right? If you have the goes to infinity, ... right? If you pick a different center, which we did not do in any of the examples today, but I am planting a seed for the next thing in the course. If you center your polynomial or base the polynomial that you build around some other location, so like that point of tangency for the tangent line was somewhere other than 0, like at 2. If it was centered somewhere else, then the structure is actually the same, but different, of course, right? So like this, it's just based at c instead of at 0. And then over here, you see that there's this part that changes. So it's like kind of like a transformation, right? You're sliding, oh, I didn't write that term. You're taking this and moving it over c units because it's based off of c, okay? Now the thing I wrote in red is called a Taylor polynomial. So Taylor, as a mathematician, had the idea that we could generalize this and not only have to use 0. Maclaurin didn't have that idea. Maclaurin thought, okay, I'm going to base everything around 0. Now, honestly, which of these is more general? The red one, right? The red one is more general because I could just let c be 0 and then I'm good to go. So because the second one is the more general case, all of this gets called Taylor polynomials. And when you have an infinite number of terms, instead of ending at n, if you have an infinite number of terms, it's then called a Taylor series. And all of these, the Taylor polynomial is clearly a polynomial, and the Taylor series is just an infinitely long polynomial. Wow. Okay, thanks for hanging in there. I know that was a long lesson, but it really is so very cool. So there's the big reveal. There's the big ta-da. We solved the mystery. Well done.